We have an additional identity here, which is actually more complicated to be proven using some of the concepts that we have learned in the calculus. We have here the limit of the natural logarithm of 1 plus z all over z as z approaching to 0 is equal to 1. This is true, right? In the concept of the calculus. And this time we are using the same structure, but this time we're using the complex number z. And of course, let us show that this is true using the L'Hopital's rule. But for the L'Hopital's rule to be used, we need to show first that it's really indeterminate as we try z approaching to 0. So let us have here the limit of your natural logarithm of 1 plus z all over z as z approaching to 0. As we try here, our z equal to 0, this is actually the natural logarithm of 1 plus 0 over 0. Our denominator is already 0. So let us try to show that the natural logarithm of 1 would actually be 0 in itself, right? So this is just equal to 0 over 0. The natural logarithm of 1 is equal to 0. If you're not convinced with that, the idea of the natural logarithm tells us, okay, or the concept of just simply, if we talk about natural logarithm of 1, it could be in the form of logarithm of 1, right? When can we get 1 on whatever base that we have? It's actually when the value of this is equal to 0. So any base. But since it's natural logarithm, this is only true, okay, when we have here this is connected to e to the power of 0 being equal to 1, because that's e is the base of our natural logarithm. So this is true when is it equal to 1, when the numerator is 0. That's why we have 0 over 0, or again, indeterminate form. With that, now we are guaranteed for it to be indeterminate. We can now use the L'Hopital's rule. So let's take the numerator, the natural logarithm of 1 plus z, as our f of z, and our g of z, the denominator z. Now, take note, we are getting the first derivative of our function. And please do not forget the derivative of a natural logarithm. So what is the derivative of a natural logarithm? It is actually a rational expression 1 over this function there. So you have 1 plus z. If you're not convinced with that, you can always try looking for the rule of the the derivative of a natural logarithm. It's actually, if you have here general form, the derivative of your natural logarithm of, let's say, z is just equal to 1 over z. But this time our z is 1 plus z. That is why we have here a rational expression of 1 over 1 plus z. Now, let's proceed to the second one. The natural logarithm, the derivative of g of z is just equal to 1. Since this is not equal to 0, we can now use the L'Hopital's rule, because this is also guaranteed, a guarantee or a need or a necessity in order for us to use the L'Hopital's rule, because if we talk about the ratio of derivatives, it should not be undefined as well. So what does this tell us now? According to the L'Hopital's rule, the limit of the original function, the natural logarithm of 1 plus z over z as z approaching to 0, which was originally indeterminate, is just equal to the limit of the derivative 1 over 1 plus z all over 1 as z approaches to 0. Okay, so of course this is just equal to it is over 1, so we just simply have here 1 over 1 plus 0, 1 over 1. It gives us a value of 1. Okay, so cutting all of this short, you will have here hence, or therefore, the item we're trying to prove, the limit of the natural logarithm of 1 plus z all over z as z approaches 0 is obviously equal to 1. Yes, that is also true for complex numbers. And again, we're using here the L'Hopital's rule to prove this further. So once you will see expressions like this later on, it's now safe for you to say it's really equal to 1. But it is only true if we have here 1 plus your denominator. If they are not the same, definitely you cannot invoke this identity. Again, we use here these concepts, especially the L'Hopital's rule in proving such. Thank you very much for watching.